Summerland Pier. The offshore oil industry did not begin with a floating platform or a steel giant. It began with a wooden pier. In 1896, engineers working the oil fields of Santa Barbara, California, noticed gas bubbles rising from the Pacific Ocean and drew the correct conclusion. The petroleum formations on land continued beneath the seafloor. Their solution was to extend land drilling technology directly into the water, driving wooden pilings into the seabed and building derricks on top, connected by plank walkways to shore. The drilling method was cable tool, a technique involving dropping a heavy iron bit on a rope repeatedly to pulverize rock. At their peak, these pier operations across the Santa Barbara coast involved 14 separate piers, 22 companies, and 412 wells. A winter storm in 1903 destroyed much of the wooden infrastructure, and the concept was finished as a viable extraction method by 1906. What the pier established was the foundational proof that oil beneath the ocean floor could be reached. Every rig type that followed is a more sophisticated answer to the same question these wooden structures first posed. Submersible barge. The submersible barge was the first mobile offshore drilling unit, and the logic behind it was purely economic. Fixed structures built over exploratory wells were expensive, and most exploratory wells found nothing. The submersible barge solved this by separating the drilling function from the foundation. The lower hull is flooded with seawater until it rests on the seafloor. The upper deck remains above the waterline, supported by vertical legs. When drilling is complete, the water is pumped out, the hull refloats, and the entire structure is towed to the next location. The design works only in shallow water, typically less than 40 feet, because the hull must physically contact the bottom to become stable. The most historically significant example is Mr. Charlie, completed in 1953 and now preserved as a museum in Morgan City, Louisiana, which drilled over 200 wells across its 32-year career. The submersible barge largely disappeared as the industry moved into deeper water, but its contribution was demonstrating that a mobile, reusable rig was commercially superior to fixed infrastructure at the exploration stage. Jack-up rig. The jack-up rig is the most numerous mobile offshore drilling unit in the world, with more than 540 in active operation. Working water depths from shallow coastal zones to around 190 meters. It is a floating barge fitted with steel legs that extend through the hull. The rig is towed to location with its legs raised. Then the legs are lowered to the seafloor, and the jacking system lifts the hull itself clear of the surface to a height above the highest predicted wave. At the base of each leg is a spud can, a broad, rounded footing that distributes the rig's weight to prevent the legs from punching through soft sediment. A punch through failure, where a leg drops suddenly into an unexpectedly soft pocket of soil, can tilt the rig in seconds and represents the most serious hazard specific to the type. Jackups are now also used extensively in the offshore wind industry, repurposed as wind turbine installation vessels, because the same stability that makes them effective drilling platforms makes them ideal for setting turbines on shallow continental shelves. Fixed steel jacket platform. A fixed steel jacket platform is a steel lattice structure anchored permanently to the seabed by piles. With a production deck on top, it does not move, is not designed to move, and many have operated continuously for more than 40 years. The jacket transfers all loads from deck equipment, waves, and wind down to piles driven typically 100 meters or more into the seafloor. Because jackets intended for deep installations are too large to be lifted vertically into place, they are built horizontally on barges and launched by controlled tilting, sliding into the water, and then upended by flooding the legs. The limitation is depth. Beyond approximately 500 meters, the steel required to resist wave loading makes the structure economically impossible. The Bullwinkle platform in the Gulf of Mexico, installed in 1989 in 412 meters of water using 77,000 tons of steel, represents the practical outer limit of the type. No fixed jacket has been built to a comparable depth since. Gravity-based structure. A gravity-based structure uses mass rather than piles to stay in position, sitting on the seafloor under its own weight, heavy enough that no storm can shift it. The structures are almost always built from reinforced concrete, cast into large, watertight forms that provide the density required for the gravity principle to function. The North Sea, with its soft clay seabed and extreme wave loading, became the primary home of the type. Gravity-based platforms there are built in sheltered fjords using a continuous concrete pouring process that produces seamless, watertight legs. The Troll A platform installed off Norway in 1996 weighs 1.2 million tons, with ballast stands 472 meters tall, and is the heaviest object ever moved across the surface of the Earth. Its legs are hollow and large enough to contain industrial equipment at depths of 300 meters below the surface. Compliant Tower. The Compliant Tower occupies the gap between a fixed jacket and a floating system, designed for water depths between 400 and 900 meters, where a rigid jacket would require too much steel and a floating unit would be unnecessarily complex. Where a fixed jacket is engineered to resist ocean forces by not moving, a compliant tower absorbs them by moving in a controlled way. The structure is a slender steel lattice, anchored by piles that deflects laterally by several feet when struck by a large wave, and then returns to position, dissipating energy through movement rather than stress. Fewer than 10 have been installed worldwide. The Petronius platform, installed in 2,535 meters of water, held the record as the tallest freestanding structure in the world at completion, with 88% of its 640-meter total height below the waterline. During Hurricane Ivan in 2004, waves near the local 1,000-year storm level struck the platform and permanently deformed several structural members while leaving the facility within safe operating limits. Drillship. A drillship is a self-propelled vessel with a drilling rig mounted on its deck and a hole through its hull called a moon pool, through which the drill string descends to the sea floor. Modern drillships operate routinely in depths exceeding 3,000 meters. The critical technology is dynamic positioning. A drillship cannot use anchors in deep water because anchor chains of sufficient length would snap under their own weight. Instead, computer-controlled thrusters distributed around the hull continuously counteract wind, current, and wave drift, keeping the vessel within a defined radius of the wellhead below. The technology was first demonstrated in 1961 by the vessel CUSSI, a converted war surplus barge that maintained position in 3,500 meters of water using manually operated outboard motors and seafloor sonar buoys. Today's drillships displace up to 100,000 tons, carry accommodation for 200 crew, and can drill to depths exceeding 10,000 meters below the seafloor. Tension leg platform. A tension leg platform floats, but it is not free to move vertically. The hull has more buoyancy than its own weight, and steel tendons anchored to the seafloor prevent it from rising, holding the platform in a state of permanent downward tension. This eliminates vertical motion almost entirely, while allowing lateral movement within limits defined by tendon length and elasticity. The practical consequence is significant. Because the platform does not heave, wellheads can be located on the deck rather than on the seafloor, allowing engineers to access and service wells using surface equipment rather than remotely operated vehicles. Tension leg platforms operate in water depths from around 300 meters to nearly 1,500 meters. The primary engineering risk is tendon fatigue. The tendons are under continuous high load, and wave-induced resonance can introduce microscopic cracking over years of operation. A tendon failure creates asymmetric buoyancy that requires immediate production shutdown. Spar platform. A spar platform is a floating production facility built around a single large vertical cylinder, extending 150 to 200 meters below the waterline. The lower portion is filled with solid ballast, placing the center of gravity well below the center of buoyancy, which makes the spar inherently stable against tipping. The deep cylinder places the hull in water largely unaffected by surface wave action, since wave-induced motion diminishes exponentially with depth. At 150 meters, conditions that would toss a surface vessel have negligible effect on the spar. Spars operate in water depths from around 600 meters to more than 2,400 meters. Installation is distinctive. The cylinder is built horizontally, towed to location on its side and upended by pumping ballast into the lower section until it rotates vertical. The Perdido spar in the Gulf of Mexico, installed in 2010 in 2,450 meters of water, is the deepest floating production platform in the world, serving 3 separate deepwater fields through a subsea pipeline network spanning 44 kilometers. Semi-submersible rig. The semi-submersible is the dominant floating drilling platform for deepwater operations. Large pontoons at the base are flooded until they sit well below the waterline, connected to the surface deck by vertical columns, producing a platform that experiences a fraction of the motion a surface ship would in the same sea state. Semi-submersibles can be moored with anchor chains in moderate depths or held by dynamic positioning in deeper water. The type is more stable than a drillship in rough conditions because the column and pontoon arrangement resists motion more effectively than a ship hull, though a drillship moves between locations faster. More than 200 semi-submersible rigs have been built since the type was first developed in the early 1960s, operating in the Gulf of Mexico, the North Sea, offshore Brazil, and West Africa. The Deepwater Horizon, which sank in the Gulf of Mexico in April 2010 following a blowout at the Macondo well, was a semi-submersible. The disaster killed 11 crew members and released 4.9 million barrels of oil over 87 days, the largest marine oil spill in recorded history, resulting in a complete restructuring of deepwater drilling regulation and a fundamental redesign of blowout preventer systems across the global industry.